Oh, I got somebody's periodic table and some paper, so I'm assuming the paper underneath it is. Okay, yeah. Put your name on it now so you don't forget later. Oh. Hey. Okay. Physics of the very small. Okay. So, the physics of this very small, we're talking about quantum mechanics. Okay. When things get really small, you have to take into account that they behave both as a wave and as a particle at the same time. And the more you try to force it to behave like a particle, the more it behaves like a wave. Because if you try to force it to go through one slit or the other, it's going through both. Okay? But if you leave a big open area, you'll see the whole rainbow of colors. Okay? So when you try to force it to make the choice that it's got to be a particle, it says, no, 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 I'm a wave. Okay? But we know it's got to be light has to be a particle too because of photoelectric effect. So the photoelectric effect proves that light's a particle. And what proves that light's a wave? Come on, you can make the rainbow connection. It's the spectrums and the interference patterns. Okay, remember the rainbow is really just an interference pattern of all the colors. We saw the interference pattern of the red, where it's striped red and black alternating. Okay, so that's proof that light is a wave because it makes an interference pattern. How do we know that a electron's a particle? No, particle. So particle, actually, the bizarre one. It's bizarre. We haven't talked about the experiment, but here's the fact that it's a particle. It's got a unit of charge. It's got a piece of charge, right? -1. There's a piece there, right? So, and it's not -1.2 sometimes, -0.8. It's always -1. That gives you the idea that it's a particle. How do we know that the electron's a wave? Because it made that interference. To the double slits, it made the interference pattern. Okay? So the electron, they could get to behave just like light. And then they tried heavier things. They tried a proton. Had to find some narrower slits because it had to be wide enough to go through both at the same time. And it was a wave. And they tried whole atoms. Every time they tried something, it came out as a wave. I think they got up to like number 50. They made interference patterns for up through number 50. But as the wave gets bigger, as the thing gets heavier, the wave gets shorter. So you got to get your slits closer and closer together. So that's your challenge, is that if the wave is shorter than the space between the slits, then it can't go through both at the same time. Does that make sense? So that's the challenge of seeing the big things. So what are we? Okay, we can treat ourselves as particles because we're never going to find a slit small enough for us. Okay, but right, that we could go through both slits at the same time, because our wavelength would be so short that the slits would have to be so close together. Okay, but when does it stop? When does it switch from being a wave to a particle? And the answer is they don't know. It doesn't. It's both a wave and particle all the time. Just depends on whether you can test it or not. So, and quantum mechanics is based on probability. Okay, and this is the part that Einstein hated. God doesn't play with dice. Well, apparently, odds are he does. It's all about probabilities. The fact is, the movie said it was a probability wave. That the wave we're talking about is a wave of where you have a chance of finding the electron. That sounds like a wave to me, right? Hey, But underneath all of this is something called the Heisenberg uncertainty principle. Okay, there are lots of aspects to the Heisenberg uncertainty principle. Lots of aspects. I already talked about one earlier, that the fact that you couldn't know up and down spin and left and right spin at the same time. Okay. Fact is, they actually did the in-between angles. So they did a 45-degree angle. Okay. And half went, and what they found was 45% went, or 50% went up, 50% went down. Okay. So that the ones that went up, knowing that it went up, when you put it at the diagonal, you still knew it was up. And you got a little tiny piece of, and some of them are down, some are left and up. That was, and on the diagonal, you could measure that, but you couldn't do the right and up. But you can get probabilities out of that. The probability that the spin's going to be there. Okay? But there's lots of aspects to Heisenberg's uncertainty principle. This is the one that people talk about most often because they can give a concrete example of why it's difficult, although the underlying physics is actually even more bizarre. It is impossible to know exactly the speed and position of a particle. And speed would be energy. So another way of saying this is impossible to know both the energy and position of the particle. Okay? So we're never going to be able to say how much energy the electron has and where it is at the same time. Okay, I'll give you a physical meaning, but it's actually because they're quantum quantities. Okay? And the way it works, the better we know one, the less we know the other. So the better I know where it is, the less I know about how much energy it has. And the better I know how much energy it has, the less I know about where it is. I think. And I'm pretty sure about that uncertainty. Okay. And what it comes down to, and what the underlying feature is, the act of measuring something changes the thing you're measuring. We don't see it really often. But you can't measure something without changing the thing you're measuring. Say, whoa, Mr. Green, I can put a ruler on top of a table and measure it. Okay? But every time I touch that table, a little bit of the table's getting rubbed off and a little bit of the ruler's getting rubbed off. Right? Every time they touch. So if I don't touch, then I can't be exact. I got to estimate, got to try to line it up and see where it was. And I saw that example up by, it was really strange. I worked at a liquor store to pay for college, one of the things I did. And this store had been around since 1900. And they hadn't changed the floors. So there was actually grooves in the floors from where people had walked for 80 years. The act of walking changed the floor. And we all know our shoes wear out when we walk on stuff, right? Well, the act of walking changed not just the shoes, it also changes the floor. Because every time it rained, we had these two streaks of water, like puddles, where people were standing in line. Okay? Now, we don't see it all the time. Okay? But it's obvious when you get to the very small. You're not going to see it in macroscopic objects, things you can see. Okay? So to measure where an electron is, we use light. Right? Because I need something smaller than the electron to figure out where the electron is. I cannot figure out where the electron is with a meter stick. It's too big. I need something smaller than the electron to figure it out. And the only thing smaller than the electron is light. But what happens when light hits an electron? Sometimes they come off, sometimes they change energy levels. But the light moves the electron. And hitting the electron changes the frequency of the light. So how good a measurement are you going to get where every time you measure, the thing you changed, the thing you're measuring changes, and the thing you're measuring with changes? Are you going to be able to get precise information that way? Imagine every time you laid down the ruler, it got a little longer. You wouldn't be able to say exactly how long it was. You could try to figure out how much it had changed, but you wouldn't be able to say exactly. Okay? So if I got an electron moving along, and a photon hits that electron, the photon changes wavelength, the electron changes velocity. Okay? So if I want to say where the electron is, I got either energy or position. If I want to say where it is, I want the shortest wave possible. Because I want to know which wave hit, and the shorter the wave I make, the more precisely I can say where it is. Okay? But photons with really short waves, what's their energy like? Very high. So when the photon hits that electron, it knocks it flying. Are you going to get any idea about how it was moving before you hit it? No. So you lose the information about how it was moving because you hit it really hard. So the more I know about where it is, the less I know about how it was moving. Okay? Now the opposite. What if I wanted to measure the energy? Then I'd want to change the energy as little as possible when I hit it. So I'd want to use a long wave. And with a long wave, where is it in that wave? Okay, you got at least one wavelength of you don't know. And the longer you make that wave, the better you'll know the energy, the less you'll know the position. So knowing where it's at stops you from knowing how it's moving. And knowing how it's moving stops you from knowing where it's at. And that's why we have electron clouds. Okay, that's why we're limited to electron clouds, and it will never get better. We're not doing percentages because we don't know more. We get percentages because that's how the universe works. Better tools won't get us any closer. Okay? There's a limit to what we can know. And there's, like I said, there's a bunch of things that are tied that way. That the better you know one, the less you know the other. We only works on really small stuff. Okay? So, let's do a quick review. Give me a second here. Okay. So, let me take you on a history. I had it open. Take a second. Okay, so you saw this yesterday. So if you shoot light at an atom of hydrogen, okay, you can see what the spectrum looks like. Let's do it fast so it shows up fast. Okay, and you'll see that the spectrum of hydrogen has a few over here. Come on, there's some other ones showing up. There should be some over here too. There should be one right about here. Come on, hit it, hit it, hit it. Okay. All right. Okay, it's individual bars. Okay. So, let's look and see how our models of the atom would work. So Dalton, okay? Dalton, with his billiard ball, just a sphere, hard sphere, didn't know anything about the atom. If an electron hit his, it would just bounce off. Which ones would bounce off? Well, everything that hit it. Okay, so you'd get the whole spectrum if it was a billiard ball. Do you get the whole spectrum? No. So the atom is not like a billiard ball. Okay, okay, classical solar system. Okay, we said it worked like a solar system, but if it worked like a solar system, oh, sorry, I did plum pudding first. Okay, plum pudding, let's speed it up. Plum pudding, see what happens to the electron when it hits, and then when it gives off light. So they're saying that the electron moves around inside that atom and then gives off light. But it only can give off one kind of light because it can be everywhere in that atom. So you'd only get one bar of light on your spectrum. Will you get just one bar? No. So we know that's not right. Okay? Next we said the solar system. But in a classic solar system, that's what's going to happen. It's going to spiral in until it does electron capture and gives you lots of energy. Because the Earth is slowly spiraling into the sun. Because as we go through space, we run into stuff, and that stuff slows us down. And if you go slower, you move closer. So the Earth will spiral into the sun. Good news. Good news. The sun will blow up before we spiral into it. So the sun will, well, you got a few billion years, so you're okay. You got time to worry about it. Time to move to another planet if you got a few billion years. Okay, right. So we know it's not that. So Bohr said it's like a solar system except the rings are fixed, and the electron jumps around when it gets hit. And notice that it gave off a red one when it went from there to there. And now let's start collecting this. Okay. So, hey, that looks like the kind of spectrum we get. Bohr worked really well for hydrogen. But as soon as he tried helium, it didn't work. Does that make sense? So he knew it was wrong because he couldn't answer, why are there levels? Because there are. Because they only give off one kind of light, so I know there are. Why? I don't know. Then a man named de Broglie said, hey, maybe you should think about them as waves. It's number of vibrations. Okay? One set of vibrations in the first energy level, two sets in the second level, three sets in the third level. Okay? Waves explain that away. Except, how do you say where a wave is? Well, you write the equation of the wave, which is what Schrodinger did. And when he wrote the equation of the wave, you got to look carefully because it's just blue tints. Hey, that's a p orbital. Come on. Nope, there's another p over here. The orbitals are there, they're just unoccupied. So that's why we talked about highest occupied level. The electron has to jump up to one of those places. One of the places it jumps is an s orbital. One of the places it jumps is a p orbital. It can go from the p to the s in the same energy level. It can fall any of those ways back. It explains why we get paired lines. Bohr couldn't explain paired lines. We get paired lines because two electrons in the same place are going to have about the same energy. It's going to be a little bit different, so it explains why we get paired lines. Because they can be in the same place at the same time. Okay? So, hey, there's another p orbital. Okay? An s orbital would just be a bigger sphere because right now it's got one s there. That looks like 2p. Maybe that's 3p. If you'll notice, the bigger ones have multiple little pieces. That's because they're waves. Okay, that's because they're waves. So the P that we draw, we say 3P is bigger. It actually has a couple of waves inside where it's big area, small area, big area. Okay? So that's what's really going on. Okay? All right, so I can stop that.